So my first few examples applying the equations of motion is to use things algebraically first, and then we're going to look at applying calculus. But both methods really help you build some of your logical thinking processes with problem solving. So they're both beneficial. The very first example, this is lecture 3 handout page 1. And the very first one is a car slowing down from a speed of 25 meters per second, and it comes to rest in a half of a second. How far did the car travel during that time? Okay, so let's see first what we have. I have a v initial, so I have v naught, then is going to equal 25 meters per second. And I am definitely given time equals 0.5 seconds. And here's the key that a lot of new students miss. This comes to rest. So when you see that, what you're told is that the v final is 0. There we go. Cool. So I know a v initial, I know a v final, I know the time it took me to get there, and I want to know this delta x. How far did it go? So let's take a look at what we have. With these two pieces of information, I immediately look at that and say, okay, I have acceleration. I can use this information to get there. And I look at the one thing that involves velocity and acceleration and time, and it does not have position. Oh, that's not very helpful. Then I look at this. Let's see. This involves acceleration and initial velocity. So if I don't have acceleration solved, I can't jump right to that. And then I come here, and it's the same thing. It needs the acceleration component in order to get to my delta x. So I'm kind of going to need to do this in 2 steps. But let's see if we can't make that a little not as daunting as it might sound. So let's write our top equation, our v final, minus, I'm moving the v initial over to the other side, minus v initial equals at. So I have v final, I have v initial. Let's go ahead and remind ourselves that v final is 0. So we don't need to worry about that. So this just gives me an equation in terms of the initial velocity and the time and the acceleration. So I can rearrange that and say that v initial divided by time will give me my acceleration. Now I look at this, I have a way to express acceleration, and I have a change in position here that involves the initial velocity, which I have, and then now I have an expression for acceleration, so I can use that. This one here, well, I also have these 2 pieces, so I can use either of those, right? I know what my final, I know what my initial, I know what my acceleration is in terms of an expression, and I want my delta x. So it's really just a preference here. So I'm going to rewrite the second equation as delta x equals v naught t plus 1/2 at squared. So I can make this substitution then and say that my delta x then equals v naught t plus 1/2 a, it's this piece, 1/2 negative v naught over time times time squared. And if I want, I can go ahead and simplify that. I can notice that I have a square here and a time at the bottom, so I can rewrite this as delta x equals v naught t, and that negative is going to come out minus 1/2 v naught t. What? So what happened here? I'm going at some initial velocity for a period of time, and I'm accelerating, but I am slowing down. So this is the expression for my acceleration piece, slowing me down to a stop. Now the beauty of creating this is that when I go to do my button pushing, it's simplified greatly. So let's go ahead and put our numbers in then. So I get delta x equals my initial velocity is 25 meters per second times my time of 0.5 seconds minus 1/2. And what do I have? V naught is 25 meters per second times my time again times my 0.5 seconds. Cool. Notice that this whole thing here, that 1/2, remember that came from when we derived it in terms of integration. So I would have something with respect to t integrated, and that gives me that 1/2. So I have 25 times 0.5 minus 0.5 times 0.5 times 25. So my delta x is 6.25 meters. There you have it.